and we are back, and we are going to go through our exam practice question 2, Helmholtz coils. So we see that we have, from Biot-Savart law, we have an equation here. It's a function of, let me just erase that, the number of turns. There's a constant here. Mu naught is the permeability of free space. I is the current. R is the radius. I want 10 millitesla, uncertainty of no more than 1 millitesla. So my number of terms nominally is 500. Winding is by hand, accurate plus or minus 10 kerns. We have this as our constant here. Measure the current through the pair of coils 35 times. So there's going to be some precision error in the current. There's going to be bias error, or actually there's uncertainty in the number of windings. What else? Divided by standard deviation here. There's uncertainty in the radius here. Ruler, there's also precision error in essentially the radius as well. 14 times. You can assume that we're perfectly at R over 2. No uncertainty. Let's see, here we go. And found the mean to be this. I need to just delete this one. My ammeter is accurate up to 1 milliampere. So there's also some uncertainty in the I as well. So let's go ahead, measure the current. Actually, there's some precision error. And also measure the radius. Yeah, there's also some precision error in, actually we already determined that. There's precision error in I as well. Do we have any precision error in the number of windings N? I don't think so. So we can go ahead and we can start to work through this problem. So we know how to do our uncertainty. So let's go ahead and set up our expression. So let's go ahead. I'm going to drag this a little bit over here. So our fundamental expression is basically B field is equal to 8 times mu naught times big N times big I divided by 5 times square root of 5 times my radius. And we also know that our mu naught is equal to 1.257 times 10 to the minus 6. So we've got this. We know that there's going to be some uncertainty, so I'm going to actually define it right now. So dB, d n is going to be derivative of B field with regards to big N. We also have dB current through here, measure with the ruler, so dB dr equals derivative of B field with respect to R. And then we also have dB di, because our ammeter is accurate to mil, that one, so we have that derivative of B field with respect to, B field with respect to big I. And there we go. So we can also do now, I also know that the uncertainty of my I is equal to 1 times 10 to the minus 3. I also know the uncertainty of my radius. A ruler, I'm just going to assume that I have millimeter tick marks. So 1 times 10 to the minus 3. And there's also some uncertainty in, what else do we have here? Uncertainty in the number of windings, which is just 10, or number of turns. Great. So we can actually do bias right now. I usually don't do this, but let's go ahead. Let's say my bias is going to be equal to square root of dB dn times uncertainty in n divided by my B field, because I want it in fractions, squared, plus, now you can copy and paste this. Let's go through here. There we go. So I've got this. Now you can paste. So dB dr, uncertainty in R, and then I. And there we go. Let's leave that. And we can actually, we'll get to that in a second. So let's look at some precision values here. So we're told, so the current, so Ni is equal to 35. We're told that the nominal value, so basically Xi is equal to 5. Si is equal to 0.1. We're also told that we have number of ruler is equal to 14. X of radius, I keep saying ruler, my 7.5 times 10 to the minus 2. And SR, my radius, is equal to 0.1 times 10 to the minus 3. And that's it. So those are our two basically precision errors where we're not told anything about measuring essentially this number of turns all those many times. So now I can say that my precision error in I is equal to, and then I need to do my quantile. This is 95%, so let's go ahead. Quantile, we need student t-distribution. We need to specify that it's going to be Ni minus 1, and then we're going to do 1 minus our alpha, which is 0.05 divided by 2, because it's two-tailed, times S of I divided by basically square root of Ni. And then we're going to do that whole thing, remember, divided by, normalized by Xi. And there we go. So that's our precision error there. For our radius, all we're just going to do is change this. R times SR divided by NR. And then here we go. Fantastic. So precision error. And then now we can actually go ahead and we can say my total uncertainty, U, is going to be equal, E total, or U B field, is going to be equal to square root of Pi squared plus PR squared plus my bias squared. And what I can do is just simply take my UB field slash dot big I goes to Xi, big N goes to the value, which is just 500 turns nominally, and then my radius goes to XR. And there you go. So we have about 2.5%. It looks like that we're dominating, and we can actually take this. We can take this code right here. We can put it here, and we can say bias. And our bias is basically really dominating this behavior. So we can change essentially that plus or minus 10 turns. We can increase our resolution on our ammeter. We can increase our resolution on our ruler. And we can see actually that would change depending on, so if we would use 1 times 10 minus 6, it might be different. Fantastic. Did I meet my aim? So let's see. We can actually calculate it out now. So I can say, for example, I'm going to say B field, because we wanted 10 millitesla. So my B field slash dot is this. Oops. So B field is about almost 30 millitesla, so we made that. We wanted an uncertainty of no more than this, so we'd have this times, if I want the uncertainty, it'd be, which is definitely less than a millitesla. So we did it. Fantastic. I can verify the calculation by placing a small test coil wire at the location of R equal over 2. I apply essentially a rotating magnetic field, and I can relate the strength of the magnetic field to the EMF, the voltage induced by the Faraday's law. Relates EMF voltage to magnetic field strength to measure. I'm going to use the instrumentation amplifier, amplify my signal as well. It's a rough measurement, so won't apply any filtration. Plot the EMF as a function of voltage on my lab VI. Calibrate my test coil permanent neodymium permanent magnet. So draw essentially this generalized measurement diagram for measuring the magnetic field strength with a test coil. So we have to kind of go and see what's our measure and. So we want to figure out the strength of magnetic field. So I want to measure my B field. There's a calibration step, and that calibration is right here using that permanent magnet. So I calibrate, And then I go to the first stage, which is your sensor transduction. So what we're doing is we're actually basically, I'm looking at, so I'm trying to measure a B field. I'm going to convert it to an analogous signal first, and that's going to be my EMF voltage of my test coil. So I put a little, like, you have basically a system like this. I put a test coil here and I look at the resulting. So I'm basically measuring with the instrumentation amplifier. So one goes to the positive, one goes to the negative terminal, and I'm actually measuring what that voltage is. So I'm converting it first to here. There is the sensor, this is the sensor transduction stage, your signal processing. There is some amplification, and there's also probably some, basically a voltage to a B field calculation as well. And then your readout is just going to be on our LabVIEW VI. So there you go. That's it. Finally, work with the ANOVA XLS file to determine which variables are statistically significant, determine the size of each variable, and the experimental conditions to maximize output. So I'm going to need to utilize here, we have needs ANOVA. I need to find this file, which will be here. There we go. And I'm going to go through here. And I'm going to say import. I'm going to call this DAT. Actually, let's go up here, because I'm going to use this similar syntax. So I'm going to say DAT equals import here. And then I'm going to go here. And I want to look at what this looks like first. And that's going to be... All right, let's open this up a little bit more. So we can see we have some factor 1, factor 2, and an outcome. So this is a two-way ANOVA. So I want to, before I even run this, remember we can do DAT. I'm going to say, give me from 2 to -1. So give me the second row to the end. And I want to look at, actually, the first thing I want to look at is the first row. Factor 1, factor 2. So variable 1, variable 2, and then our outcome. So now what I want to do is say, I want to say take... we'll say DAT, give me all the rows, the first column, and I want to say delete duplicates so I can look at delete duplicates. And I want to see what's in here. So I have 5 conditions because factor 1 is my variable. I can look at the second column and I can see I only have 2 conditions there. So what I'm going to do is I'm going to take my ANOVA, I'm going to put in DAT, give me all of the, basically from the second row all the way to the end of my list. I'm going to call this F1. I'm going to call this, basically, F1, F2, and then that's it. So only 2 variables here. And then I'm going to specify again F1, F2. And let's look at what we got. And I'm actually going to do also post tests and then Tukey. All right. So what variables are statistically significant? Both of them. P-values are less than 0.05, assuming that we're working on 95% confidence interval. Fantastic. What else do we have here? We need to see what the size of the effect is. So remember, it's going to be our sum of squares. So for F1, sum of squares divided by sum of squares of that variable plus sum of squares of our error. So that's a very large effect. Now what about here? Let's do, this is our sum of our squares here. Here. That's probably a bordering on small effect. So this is statistically significant, but the effect size is small. Excellent. Now, what is Tukey telling us here? The Tukey is telling us here that all of these are, 1 is different from 2, 1 is different from 3, 1 is different from 4, 1 is different from 5. And let's look at all of these values here. Let's look at them because it might help us to focus in on. Here we go. All right. And here's where it's telling you F1 here. So if I want to maximize my conditions, I definitely probably want to pick but 4 and 5 are very close. So I want to pick 4, but is 4 different from everything else? So 4 is different from 1, 4 is different from 2, 4 is different from 3, but 4 is not different from 5. So I want to pick 4 or 5. And for 2, they are statistically significant. So now I've got F2, B. So there you go. That's it. Thanks. And see you next time. Actually, we answered all the questions. See you next time. Thanks. Bye.